Video we're going to continue the topic what makes a car stop. We're going to be looking at momentum, impulse and collisions.
In this video we're going to be looking at conservation of momentum, impulse and collisions. So what we're actually going to be looking at is the physics behind car crashes. So to understand the physics behind car crashes, the first thing we need to understand is momentum. Now, momentum is a vector, so like force, velocity or acceleration, it's got a magnitude and also a direction. So momentum can be calculated as the product of the mass of the object and the velocity of the object. So momentum is generally given the symbol a lowercase p. So our formula for momentum is P is equal to mv. The units for momentum are kilogram meters per second or Newton seconds. So the definition of momentum is in alignment with our everyday usage of the word momentum. We tend to say that heavy objects such as trucks have a lot of momentum, and then lighter objects like a toy car have a lot less momentum. So momentum is just the product of the mass and the velocity. Let's do an example now where we will calculate the momentum of an object.
So this question says, a truck has a mass of 7,000 kilograms and a car has a mass of 1,200 kilograms. Both are travelling northward at 110 kilometers per hour. Calculate their momentum. So in order to calculate their momentum, we're going to need to use the formula that the momentum is equal to mass times the velocity. So first of all, we'll need to convert this velocity into the velocity in meters per second. So the velocity is equal to 110 kilometers per hour, which is equal to 110 times 1,000 meters per hour. And then to convert it into seconds, we divide by 60 times 60, and that gives us 30.56 meters per second. So in order to calculate the momentum of the truck, we have that the momentum of the truck is equal to the mass of the truck, which is 7,000, times 30.56. So solving that on the calculator, we get 213,889 Newton seconds. Now we should probably give this to two significant figures. It's hard to tell, but this data could be to 2 or 3 significant figures. So let's give it to two significant figures. So that's 210,000 Newton seconds to two significant figures. And then momentum is a vector, so we should also give a direction. And so since the velocity was northwards, this momentum is also northwards. So northwards. And now we need to do it for the car. So the momentum for the car is equal to the mass of the car, which is 1,200, times the velocity of the car, which is 30.56 meters per second. So this is equal to 36,672 Newton seconds. So to two significant figures, this is equal to 37,000 Newton seconds, and that's to two significant figures. And now we also need to include the direction. So the direction on this momentum is northwards.
Now, in order to change the momentum of an object, we need to apply a force to the object. So we can actually use Newton's second law to derive the relationship between the force applied on the object and its change in momentum.
So to use Newton's second law to derive the relationship between the change in velocity and the force, we have that the acceleration is equal to the net force over the mass. That's just Newton's second law, which tells us that the net force acting on an object is equal to the mass times the acceleration of the object. Now we defined acceleration as the rate of change of the velocity. So this is just equal to the change in the velocity over the time. These little squiggly lines underneath these letters represent that this quantity is a vector. So this velocity is a vectorial quantity. It's got a direction as well as a magnitude. And so what we can do is substitute this expression for the acceleration into this formula up here. So that tells us that the net force is equal to the mass times the change in the velocity over the time. And now the mass times the change in velocity. Now we can write that change in velocity as the final velocity minus the initial velocity. That's just what the change in velocity means. And so we've got mvf minus mvi on t. And this is just the final momentum and this is the initial momentum. So this is equal to the final momentum minus the initial momentum over time. And so the final minus the initial, that's the change in the momentum over the time. And these momentums and velocities are all vectors and so should all have the squiggly line underneath them. So we've got that our net force is equal to the change in momentum over the time. So the total force acting is equal to the change in momentum over time. So we can also write this as the force times the time is equal to the change in the momentum, which is just equal to the mass times the final velocity minus the initial velocity.
So the quantity, force times time, Ft, actually has a special name. It's known as the impulse. So the equation that we've just derived, Ft is equal to the change in momentum, actually has a special name. It's called the impulse momentum theorem, and it says that in order to change the momentum of a body, we need to have an impulse. So a corollary to this is that if there's no unbalanced forces acting on the system, then there can be no change in momentum. So in a minute we'll be looking at conservation of momentum, and this occurs when there is no impulse. But let's think about what impulse tells us about car crashes. During a car crash, we have a car which is travelling at some initial velocity, and then it comes to a stop relatively suddenly. So that change in momentum is fixed for that crash, as the change in momentum is the mass of the car, or if we're considering the momentum of the passengers, it's the mass of the passengers times the initial velocity. That is the change in momentum as the car in a crash always ends up stopped. So in a crash, we want to decrease the force felt by the passengers. It's the force acting on the passengers that does all the damage in a crash. If there's no force acting on you, then there's no way that you can be hurt. So what car designers try and do is decrease that maximum force acting on the passengers. So the impulse momentum relationship actually tells us how we can go about doing that. If we want to decrease the force on the passengers, then we need to increase the time over which the passengers come to a stop. So one way that cars do this is crumple zones. Let's have a look at a clip now showing crumple zones in action.
So you can see the crumple zone increases the time for the collision. Here it is again in slow motion. So this significantly decreases the maximum force on the driver. Now if we have a side-on collision, there's a lot less crumple zone, and so it's much more dangerous for the driver.
Now that you've seen the crumple zone in action, let's look at a couple of examples of using this impulse momentum theorem.
So the question is, a driver travelling at 80 kilometers per hour sees a red street light. It takes the 70 kilogram driver 3 seconds to stop the car. What is the average force experienced by the driver over this time interval? So to use this, we're going to use the relationship between the change in momentum and impulse. The impulse, Ft, is equal to the final momentum minus the initial momentum. That's just the change in momentum. And so this is equal to m times the final velocity minus the initial velocity. Now we know that the final velocity is 0 as the car comes to a rest. So what we're going to need to do is convert this initial velocity from kilometers per hour into meters per second. So the initial velocity is 80 times 1,000 meters, and then to get it from hours into seconds, we divide it by 60 times 60, and that tells, doing that on the calculator gives us 22.22 meters per second. And so now we can rearrange this equation here to get the force. So the force is equal to the mass times the initial velocity over the time, and we've got a negative sign there. This negative sign indicates that the force and the initial velocity are in the opposite direction. So this is equal to negative. The mass of the driver is 70 kilograms. So we've got 70 times the initial velocity, which is 22.22, and over this time, which is 3.0 seconds. So solving that, we end up with 518 newtons. And so we should just give this to two significant figures, as this data is all to two significant figures. So that's equal to 520 newtons to two significant figures. And we've gotten rid of the negative sign, so to account for that, we should say in the opposite direction, to the initial velocity. Okay, let's solve another problem. So this question says, the graph shows the force acting on a 5.0 kilogram block over a 10-second time interval. At the start of the 10 seconds, the block is at rest. Calculate the speed of the block at the end of the 10 seconds. Here's the graph. You can see its shape. We've got force on the vertical axis in newtons, and on the horizontal axis we've got time in seconds. So to solve this problem, we're going to need to use that the impulse, the force times the time, is equal to the change in the momentum, which is equal to the mass times the final velocity minus the initial velocity. Now we know that the initial velocity is 0, as it tells us in the question that the body starts from rest. So now this is a bit tricky because we've been given a graph, but to work out force times time is just the area underneath the curve on the force times graph. So let's split this into 3 sections. We've got 2 triangles and a rectangle. You could just treat it as a trapezium if you want to. So force times time, and we'll go from 0 to 3 seconds, is just this area here of this triangle. So the area of a triangle is half the base times the height. So we've got half. Now the base in this case is the 3 seconds, and the height, this goes up to 10 newtons, so that's 10. And then we can work out the force times the time going from 3 to 6 seconds. In this case, we've got this rectangle here. So a rectangle is just the base times the height. So the base is going from 3 to 6. So this length here is 3, and the height is 10. So that is equal to 30. When we do this one, we end up with 15. And force times time going from 6 to 10 seconds. Once again, we've got a triangle over here, and so that's half the base. The base, we're going from 6 to 10, so that's 4 seconds. So 4 times the height, and the height is 10 newtons. So that is equal to 20. And all these have units newton seconds. So this tells us that the force times time is equal to 15 plus 30 plus 20. So that is equal to 65 newton seconds. And that is equal to the mass times the final velocity. And so the final velocity is equal to 65 over 5, which is equal to 13 meters per second. Now, if this force continued and went below the axis, that would actually be a negative force, and if that was ever to happen, we would need to subtract the area underneath the curve from the area on top of the curve. So if we had any area underneath the curve here, that would be a force acting in the opposite direction to the motion of the object, and so would be a force slowing the object down.
Now, something very special about momentum is that it's conserved during collisions. So we've said that we need an impulse in order to change the momentum of an object. But if we consider a system such as two cars which are moving towards each other, in that case there are external forces acting on them. There's friction, there's gravity, but during the collision those external forces are tiny compared to the internal forces felt between the cars. So we can ignore the gravity and the friction while the cars are colliding. So we say that the momentum of a system is conserved during a collision. So how we can write this as an equation is that the initial momentum is equal to the final momentum. So let's imagine the case where we've got two objects colliding. Then to write this as an equation, we've got m1 times the initial velocity of body 1 plus m2 times the initial velocity of body 2 is equal to m1 times the final velocity of body 1 plus m2 times the final velocity of body 2. Let's have a look at a couple of demonstrations now where we'll be showing this conservation of momentum during a collision event. So a collision in physics is when any two bodies approach each other, interact with each other, and then either end up stuck together, moving apart, or moving together. So when they approach each other and then interact, that's called a collision. So what we have here is an air track. In a minute, we're going to turn on a vacuum pump, which will blow air in here, and there's lots of little holes along here which expel that air, and this reduces the friction between the carts and the track. So let's turn it on now. Now let's have a demonstration of conservation of momentum. When this cart travels in this direction and hits this cart, let's look at what happens. So you can see this cart moved in that direction, and this cart also continued to move in that direction, conserving the momentum. Now let's have a look at what happens when both carts are moving. You can see in that case, they were both moving this way to start with and then both moving this way at the end.
Here's a slow action replay. As the carts are moving in opposite directions at the beginning, their momentums cancel out and the initial momentum is 0. Afterwards, they're moving in opposite directions, and so the total momentum remains at 0.
Finally, let's have a look at what happens when the carts travel towards each other, but instead of having bumpers on the end, they now have blue tack.
So you can see in this case, initially they're moving towards each other. After they stick together, they go at a much smaller velocity because almost all of the initial momentum cancelled out.
Okay, so what I'm going to do is stand on this skateboard here. I'm going to throw this ball, and you observe what happens to me when I throw the ball. Okay. I need to throw it.
So what happens is when I throw this ball, it's about 10 kilograms, the ball moves quickly to the right and I'm moving much more slowly to the left. I'm moving much more slowly than the ball because I have a lot more mass. Overall, the momentum of the system remains at 0.
Okay, what I have here is a cart with a hanging mass. Now I'm going to hold the cart stationary and pull the mass up here. Now try and predict what's going to happen when I let go of the mass. Okay, have you thought about it? Let's see if you were right. Okay, can you explain why that happened? What happens is that momentum was conserved. When I was holding the mass up here, stationary, there is no momentum. So when the mass comes down, the cart has to move in the opposite direction to the mass to make up for the changing momentum of the mass.
Okay, so here's an example of a problem that we can solve with the law of conservation of momentum. So the question is, a 100 kilogram man is stuck at rest on an icy pond. He has a ball with him with a mass of 2.0 kilograms. He is 10 meters from the nearest edge of the pond. If he throws the ball with a speed of 5.0 meters per second away from the nearest edge, how long does it take him to reach the nearest edge? So to answer this one, we're going to need to use the law of conservation of momentum. So the initial momentum is equal to the final momentum. And here's the pond, here's the man holding the ball. Now to start with, the man and the ball are stationary. So the initial momentum is 0. The final momentum is equal to the mass of the man times the velocity of the man plus the mass of the ball times the velocity of the ball. And so he throws the ball and the ball travels this way and the man travels this way. Here's the nearest edge here. And so what we need to do is work out the velocity of the man, and we'll be able to use that velocity to work out how long it takes him to get to the edge. So we've got that the mass of the man times the velocity of the man is equal to minus the mass of the ball times the velocity of the ball. And so the velocity of the man is equal to minus the mass of the ball times the velocity of the ball over the mass of the man. So this is equal to 2.0 times the velocity of the ball, which is 5.0, over the mass of the man, which is 100. And we've got a negative, and so we end up with negative 10 over 100, or minus 0.10 meters per second. Now this negative indicates that they are in opposite directions. So as the ball goes away from the edge, the man is going to go towards the edge. So the velocity of the man is equal to 0.10 meters per second towards the nearest edge. And now he's starting from rest, so we can use that the distance travelled, x, is just equal to the speed times the time. So the velocity of the man times the time. And so the time it takes the man to reach the edge is equal to the distance he has to travel over his speed, and the distance he needs to travel is 10 meters, and the speed he's going at is 0.10 meters per second, and so this tells us that it will take him 100 seconds to reach this edge. So 100 seconds, or 1 minute and 40 seconds. So to do this, we needed to assume that this icy pond had no friction. If there was friction, then it would slow him down and he might not actually have enough energy to reach the edge.
Now, we can classify collisions. There's 3 different types of collisions. We've got elastic collisions, inelastic collisions, and perfectly inelastic collisions. Let's start by considering an elastic collision. In an elastic collision, as in all collisions, momentum is conserved. But an elastic collision is special because kinetic energy is also conserved. So a great example of an elastic collision is with a Newton's cradle. So let's have a look at that now. What we've got here is a device known as a Newton's cradle. This is a really nice demonstration of elastic collisions. If I pull one ball up on this side and release it, the momentum is transferred through all these balls to the one at the end, which then rises to approximately the same height as this ball was initially. Now what gets really interesting is if I pull 2 balls up on this side, you can see that 2 balls rise up on the other side. If we do 3 balls, 3 balls rise up on the other side. 4 balls. And even 5 balls. So let's now try solving a problem using the Newton's cradle.
So we need to show that if one ball is swung down in the Newton's cradle device and 2 balls end up swinging up, then the collision is not elastic. So let's draw a diagram. We've got one ball, mass m, with some initial velocity vi coming down, and then we end up with 2 balls, each of mass m, with velocity vf swinging up. So each of these balls has velocity vf. So we know that in a collision momentum is conserved. So we know that the initial momentum is equal to the final momentum. And so the initial momentum is just the mass times the initial velocity, because all the other balls are at rest to start with, and then at the end we've only got these 2 balls moving, so we've got 2m, that's the total mass because there's 2 of them, times the final velocity. So that's what conservation of momentum tells us. Now, if kinetic energy is conserved, then we've got the initial is equal to the final kinetic energy, and the initial kinetic energy is given by a half mvi squared, and the final kinetic energy we've got half, and then we've got 2m, and then we've got vf squared. So let's rearrange this equation and make vf the subject. So we've got vf is equal to mvi over 2m, and so this is equal to vi on 2. And now what we're going to do is replace the vf here with this expression and see what we get. First of all, note that the halves on either side of the equation cancel and the m's cancel as well. So we've got VI squared is equal to 2 times VF squared, which is VI on 2 all squared. So this is equal to 2 times VI squared on 4. So this is equal to VI squared on 2. But we can't have VI squared is equal to a half VI squared. Unless the initial velocity is 0, that is impossible. So as VI squared does not equal VI squared on 2, this is not possible. So as kinetic energy is not conserved, this collision would not be elastic. So let's go and look at what happens when we have a collision which isn't elastic now.
An inelastic collision is one in which momentum is conserved, as it is in all collisions, but kinetic energy is not conserved. So an example of an inelastic collision is a car crash. During a car crash, the metal making up the cars deforms. There's also sound and heat energy lost. So you need energy to deform the metal. And so some of that kinetic energy is lost to other forms of energy. Let's solve a problem now involving an inelastic collision.
So the question is, a car crashes into a wall. Before the collision, the car is travelling with a velocity of 60 km per hour towards the wall. After the collision, the car is moving away from the wall at 20 km per hour. And the question is, part A, is the collision elastic? And part B, is momentum conserved in this collision? Explain. Okay, so let's draw a diagram of what's happening. We've got a wall here, and here's our car travelling towards the wall at 60 kilometers per hour. And then afterwards, we've got our wall and we've got our car moving away. Should be a slightly shorter arrow. Let's make it a bit shorter. At 20 kilometers per hour. Now, is the collision elastic? And the answer to that is no. Kinetic energy is not conserved. So we've got initially kinetic energy equals a half times the mass of the car times the initial velocity of the car squared, and the initial velocity of the car is 60 kilometers per hour, and 60 kilometers per hour is equal to 60 times 1,000 over 60 times 60. So this turns out to be 16.67 meters per second, and down here the final velocity is 20 kilometers per hour, which is equal to 20 times 1,000 over 60 times 60. So this is equal to 5.55 meters per second. And so this is equal to a half times whatever the mass of the car is times 16.67 squared. And then finally, the kinetic energy, it's mainly in the car. The wall will be moving backwards a little bit and it's attached to the mass of the earth, but that velocity is much smaller. So we've got a half times the mass of the car times 5.55 squared plus the kinetic energy of the wall. But this is very small because the velocity of the wall is very small and the kinetic energy is proportional to the velocity squared. So kinetic energy is not conserved. It will be lost through energy going into crumpling the car, etc. Now part B says, is momentum conserved in this collision, and explain. Okay, now this one isn't so obvious. The answer is yes, because momentum's always conserved in a collision. But what's happening is the initial momentum is equal to the mass of the car times the velocity of the car, which is the initial velocity of the car, which is 16.67 meters per second. And the final momentum is equal to, now the car is moving in the opposite direction, so it's the mass of the car times 5.55, but this is negative, plus the momentum of the wall. Now the wall does actually have momentum, even though it looks like the wall is fairly stationary. The wall is connected to the earth here, so the wall and the earth do move backwards a very little bit when the car hits it. However, because the mass of the earth is very, very, very large, the velocity is very, very, very small, and so you don't actually observe this movement. So momentum is conserved. Now, if you wanted to show part A a little bit more mathematically, you can take some time and prove that for an elastic collision, the initial velocity of object 1 minus the initial velocity of object 2 is equal to negative the final velocity of object 1 minus the final velocity of object 2. Now in this case, the initial velocity is 60 kilometers per hour and 0, so this is 60, and the final is 20, and we've got very close to 0, so around about 20, so clearly they're not elastic. But this equation holds for elastic collisions. You show it by solving simultaneously the equation for conservation of momentum and the equation for conservation of kinetic energy for two objects colliding.
Now we use this Newton's cradle to demonstrate elastic collisions. We can actually force it to be an inelastic collision if we use some blue tack to stick some of these balls together. In this case, if I hit it with one ball, the three balls at the end are forced to move. Or if I just have two balls, the two balls at the end are forced to move. And we've shown that in this case, that can't be elastic. In a perfectly inelastic collision, momentum is conserved and kinetic energy is lost, except it's different from an inelastic collision because the two bodies which are colliding end up stuck together. So initially they're travelling separately, and then at the end they're travelling together. So let's have a look at an air track now, where we can model these different types of collisions. So here we have a demonstration that should show a perfectly inelastic collision. What we've got here is an automated golf club to make up for my poor golf skills. It's going to hit the golf ball down here. The golf ball is going to travel over to this cone over here, where it should remain trapped, and the golf ball should stay in the cone so that they move together, so that this is a perfectly inelastic collision. Okay, let's see if this works. Yep, so that is a perfectly inelastic collision, as after the two objects had hit each other, they remained stuck together. Okay, so we're going to have a collision here. I'm going to let go of these balls. Now, as you watch the collision, I want you to think about whether momentum's conserved, and the tricky one is kinetic energy conserved.
So both momentum and kinetic energy are pretty much conserved in this collision. Initially, the big ball and the small ball have the same velocity downwards towards the ground. After they hit the ground, the small ball is travelling very quickly and the larger, heavier ball is travelling more slowly. But overall, the kinetic energy has been conserved.
So in this video, we've looked at more of the physics behind cars stopping. In particular, we've looked at the case where the car unfortunately stops in a collision. So you've met the concepts of momentum and impulse. You've seen how a crumple zone works by increasing the time for the collision and so decreasing the force felt by the passengers inside the car. You've been introduced to the idea of momentum conservation during a collision, and you've seen how collisions can be classified as elastic, inelastic, or perfectly inelastic. In the next video, we're going to be considering what happens to a car as it turns around a corner. So not really cars stopping, but that's called circular motion and is an important part of physics.
So special thanks to Sebastian Frick for filming this video, and a special thanks needs to go out to Gary and Aurelio in the demo unit for helping to put together all the demos in this video.